I'm recording the session. Okay, so you're looking at the contents of this chapter. We started a new chapter, chapter 17, and we can finish it today. Probably we'll finish it ahead of time, and then we can do some review question from past exam. So let's see what we've done so far. We covered 4 sections. We defined electric current. Anyone remembers what is the definition of electric current?
It's the flow of charge, right?
Yeah, rate of flow of charge, right? Flow of charge, I mean, how fast the charges flow. So suppose you take a cross-sectional area and watch the charges passing through this cross-section and time it and divide the amount of charge by the time taken, that will be the current. So it is coulomb per second, we call it ampere. That's the SI unit. Okay, so you need to know. Then, like that, we went to the second topic, second section. We connect the current with the drift speed of the charge carriers. Anyone remember the equation? Salman? Jury, are you there? Jury.
Miss, I'm Jude. I opened from my sister's iPad.
Oh, yeah, I know. Okay. I thought Jury is attending. Are you Jury or Jude? Okay. Anyway, Jude, please change your correctly, right? Okay. So, otherwise, I will mark Jury as present and Jude as absent. Okay, you know that. Jude, so tell me.
Okay, doctor, I changed it. Thank you.
Good.
Sorry.
Jude, tell me, what is we learned in topic 2, section 2, something. Do you remember what we learned?
Doctor, no, I forgot.
Okay, Jude Kawashki. Can you help me?
Yes, doctor. We talked about the drift speed, right? Like we connected current to drift speed.
That's right. So we had an equation there because we saw that, the charge carriers will be moving, and of course it will be related to this current. Because current is the rate of flow of charges. Definitely there must be a relation between current and the drift speed of the charges. Okay. So we had an equation there. Then topic 3, we talked about measuring the important quantities in electric circuit, which are the voltage and current. So we measure current with a certain device. What do you call that device that which measures the current? Anyone knows? Yeah, ammeter. Thank you. Thank you, Abdullah. Yes. Yeah. Somebody, Lulu, do I talk to you after the class? Yeah. Okay, Lulu. Yeah, you can. So stay, then we can talk. Okay, fine. So yeah. Thank you, Abdullah Mutan. Yes, ammeter. So what about the other one? What do we call the device that measures the voltage or the potential difference? What do you call that? Somebody else answer, please. Not Abdullah. Jude?
Yes, doctor.
Yeah, tell me. What do you call the device that measures the voltage? Come on, simple question. It's some common knowledge, right? It is not something entirely science, or even layperson should know. Measuring is meter. Voltage
voltmeter, right?
Very good, voltmeter. Thank you. So then, we saw that, if you want to measure the current, you have to put the ammeter in series with the thing that you want to measure the current in. And the potential difference of voltmeter should be connected in parallel, tap the 2 points across which you want to find the voltage, right? Then topic 4, we introduce resistance. Resistance, when you set up a potential difference across an element, the current that flows is proportional to the potential. The proportionality constant, if it is constant at all, is called the resistance. That's how we define the resistance. Then we saw that certain devices, the resistance is constant in a limited range, like metals. And then, so it is also called the Ohm's law, the definition of the resistance. Then we are in topic 5. Let me fast forward to topic 5. Okay. That is section 5, which is we did a questions on resistivity. We introduced resistivity as well. Resistivity, how does it differ from the resistance? Resistivity is the property of the material. It's a constant for a given material, okay? Unlike the resistance, resistance can depend on the length of the material, cross-section of the material, then we define the resistivity. Okay, right. Then we had this question that we did. Now we come to the new section. Temperature variation of resistivity. Resistivity of a given material, like say copper, can vary with temperature. So we got, so for most metal, this increases linearly with temperature, okay, in a linear relationship. What happens when you increase the temperature? The atoms, the fixed atom, the lattice points, they start vibrating faster. That will kind of give a resistance, more resistance, because it just increase the collision of the charge carrier. It is going to hit those atoms. Then it will reduce the current flow. The electrons are the charge carriers in a metal. They find it more difficult to pass through atoms because they're vibrating more with a higher amplitude. Okay, that's very clear. Okay, for most metal, this resistivity is approximately linearly with the temperature. So if I resistivity at a certain temperature T, you can see it's a really linear relationship. Okay, what is this thing? They compare it with at a certain point. At a certain temperature, reference temperature T0, for example, we choose the reference temperature usually as 20 degrees, a room temperature. Say the resistivity is rho 0. Then at any other temperature, it will be proportional to that temperature. And the proportionality constant is called alpha, the Greek letter alpha, and it is called we use the symbol alpha, and it is called the temperature coefficient of resistivity. Okay, so we got another equation that you'll be using to solve questions. This is the variation of resistivity with temperature. Okay, right now we can go ahead and also write an equation for resistance. What we had before was resistivity. We said the resistivity is proportional to the resistance. The proportionality constant, resistivity is proportional to the temperature. The proportionality constant is called the temperature coefficient of resistivity. Okay, but we know that these two are related to each other, and provided we have a uniform cross-section, we can say for a given piece of resistor, its resistance is also proportional to the temperature. With a uniform cross-sectional area, okay, given length of a resistor, then we can also write this equation as between resistors, not just resistivity. You know the difference between resistance and resistivity, right? Okay, resistance going to depend on the length of the cross-section, okay, of a given material, but the resistivity is constant for a given kind of material. Okay, so we move to another section, electrical energy in a circuit. In a circuit, what happened? We have a battery. So the battery will increase the energy, the electrical energy of the charges by providing its energy through chemical potential energy. So there's chemical reactions occurring inside the battery, the cell, even if it is a dry cell also. There's a chemical reaction. So the chemical energy is transferred to electrical energy to the charges. The charges will be brought to a higher potential energy from a lower potential energy, the amount that is increased is given by Q delta V. Delta Q is the amount of charge, so we call delta Q here, and it is the potential difference is increased to the charge. So the amount of potential energy change will be delta Q and delta V increase actually. Then what happened? The charges move through the circuit and it comes across a resistor. There it will lose its potential energy during collisions with the atoms in the resistor. This will obviously increase the temperature of the resistor. Thus the internal energy of the resistance will increase as its temperature. Okay, is that clear? Can I move on? So we started a new section. We are talking about electrical energy in a circuit. So the electrical energy is produced by the chemical potential energy in the cell or the battery, and it will increase the electrical potential energy of the charges as the charges move from the negative end of the battery to the positive end. So here we have a circuit diagram that shows you just as a battery, a simple diagram with a resistor. There is only one resistor connected to the circuit. So in order to keep the discussion simple, we're going to put some points. The negative terminal end is A, the positive terminal end is B. So the potential difference V delta VAB will be the voltage of the battery. Say maybe if it is a 9-volt battery, the potential difference across the terminal is 9 volt. But let's say we ground it, okay? We connect this point, the negative end, to the earth. So we can take the earth's potential to be 0. So we will have the potential absolute value, not the difference, at A to be 0. So as the electrons no, not electron, let's take the positive, okay? Actually the electrons that are moving, but it doesn't matter. We can just use the conventional current. So let's say the positive charge moves from A to B through the battery. As it moves from A to B, its potential energy will be increased by that amount we told you before, delta Q multiplied by the potential difference. Then as it goes through the resistance from C to D, that potential, the electrical energy will be dropped, okay? It will be spent as it goes through the resistance. And when it comes back, and the charge will be coming back to the negative terminal. So point A is the reference point. We grounded, so it is taken to be 0. As the charge moves through the battery from A to B, the potential energy of the system increases by delta Q delta V. Where does it get the energy from? From the chemical energy inside the battery. So the chemical energy of the battery decreased by the same amount. Now, as the charges move through the resistor, from C to D, it loses energy in collision with the atoms of the resistor. The energy is transferred to the internal energy of the resistor as thermal energy. When the charge returns to A, the net result is that the sum chemical energy of the battery has been delivered to the resistor and causing its temperature to rise. Okay, now we talked about energy. Now the next step is to talk about power. Now, what's the connection between energy and power? Anyone knows? I need to get some feedback from time to time because I'm alone here in the classroom. No one to tell me that I'm communicating it or not, please.
I know that in order to gain power, you need to work over time, and work is the same, is like equal to energy in a way. Like that's what I know.
Yeah, exactly. So we learned in the first semester, the power is how fast you do the work, right? But the work is energy. Okay, when you do work, the energy get increased. It's also the power is how you transfer the energy as well as how fast you do the work. Yeah, exactly. All right, Jude. So here we are talking about energy. So the power is how fast the energy being transferred. So we take the energy from the battery and we supply it to the resistance. So we can say how fast the energy is lost when the energy goes through the resistor. It will be, you can say that energy that is delivered divided by the time taken to deliver that energy, how fast the energy is being transferred. You know the energy delivered is this, Q delta V. The charge is delta Q, so delta Q delta V divided by delta T. How fast, rate, time rate. Like the acceleration is what? Acceleration is time rate of velocity change, how fast the velocity is changing with time. So likewise, the power is how fast the energy is not changed, transferred, okay, how fast it is being transferred, the time rate. So we can see that this is the definition of the current. So I can say the power delivered to resistance, for example, will be the current through that resistance and the potential difference across that resistor. Okay, so power is I into delta V. But from Ohm's law, what is Ohm's law? You can take this equation and say in the I delta V, power is I delta V, that is the first we start with that. I can eliminate the delta V from the Ohm's law. Oops. Ohm's law tells you delta V is the IR, so I can put delta V is equal to IR, then power become I squared over R. Similarly, I can eliminate delta V from this equation by substituting, I'm sorry, we can eliminate I from this equation by substituting I is equal to delta V over R, then you get this expression for the power. So, we'll start with the first expression, power is equal to I into delta V, but, sometimes, question, I and delta V is not given, but maybe I and R is given, delta V is not given. In that case, you use the other equation, power is equal to I squared over R, I squared into R to find the power. Okay, is that all clear, everybody? Can I move on, Jude?
Yes.
Thank you. Thank you, Abdullah. So, right. Now, what about the units for measuring the power? Okay, this is not something new. We come across this before. So, is joule per second SI unit, but joule per second has a single name, watt. Okay, again, after a scientist who worked on this electricity, James Watt, I think he's the one who discovered some other things. Okay, fine. So Jules Watt, no, not Jules Watt. Never mind, I forgot. Okay, James Watt. Okay, James Watt. Joule is someone else. Right. So after him, Watt, W-A-T-T. That is the unit for. It is actually joules per second, but we have a single name for it, watt. But remember, I must be in amperes when you use the I delta V equation, and delta V must be in volts. The unit of energy used by electric companies, on the other hand, is not joule. Okay, joule is the SI unit for measuring energy, but it's a very small amount of energy. 1 joule is negligible. Okay, if your electric company want to charge you for your energy consumption, because they charge for your energy consumption, how much joule you used. But 1 joule is a very small amount of energy. If the electric company wants to charge you for 1 joule, they will even give it free for 1 joule. It will be very small amount of cost, very little. That's why we need a big practical unit for measuring current, and that practical unit is called kilowatt hour. Okay, kilowatt hour. Now let's see what it exactly means. So joule is actually you can give it in terms of watt. 1 joule is 1 watt second. Well, you only give the watt as joule per second, but you can invert everything and say 1 joule is watt second. So what is 1 kilowatt hour? So let's convert into watt second. Kilowatt is 10 to the power 3 watt. And 1 hour is 3,600 second. So that gives me is 3.6 million watt second. 1 kilowatt hour is a huge amount of joule. Watt second is joule, right? So 3.6 million joule will make 1 kilowatt hour. Is that clear, everyone? So when it is this big, that can be charged, but still it will be just few halalas or less than a halala. Okay, right, let's see. Probably we'll do a question later. Yeah, that's on this. Now we have come to the last section in this chapter. Superconductors. It's a class of conductors, as the name implies, is super, meaning conductors conduct charges, but still it has resistance. It's not zero. There will be some resistance for the charges to flow. So you will have wastage of energy because it will be converted into the thermal energy, which is not useful. It is lost. But whereas superconductor is something that is discovered in the 1900 or something, some material seems to have zero resistance below a certain temperature. That is very good because these people got very excited when they saw that. But at that time, very early in the 1900, they saw it happens only when the temperature is very, very low, like 4 Kelvin, almost near the absolute zero. 0 Kelvin is the absolute zero, right? You cannot even reach the 0 Kelvin, but 4 Kelvin probably in the lab you can. So when the temperature is brought to 4 Kelvin, some elements, like I think it's mercury or something, mercury, mercury, right? It's a metal. Mercury is a metal, but it still has a resistance. But when it is below 4 Kelvin, it all of a sudden becomes zero resistance. So we call it superconductors, okay? Zero resistance. So the temperature at which something becomes superconductor is called critical temperature. So we have this TC to stand for critical temperature at which a material becomes superconductor. Now you see a graph here. This is for that particular mercury. Now, the value of Tc, the critical temperature in which the material becomes superconductor, is called the critical temperature. It depends on its sensitive to the composition. We can have different elements mixed in a certain proportion, then we can change the critical temperature of that compound. Pressure, it depends on the pressure. By increasing high pressure, we can bring the critical temperature up. And also the crystalline structure can be manipulated to make it superconductor at a higher critical temperature. So in a superconductor, once you have a current, it will remain there, persist without applying any battery. It will be there forever. So that is very exciting because it can have a wide range of application because the wastage is zero. You don't need extra power. Once the current is there, it is there forever. So this is because the resistance is zero. So people got very excited, when there was a breakthrough, because that critical temperature is very low, 4 Kelvin. It is not practical to have a superconductor. Only in a lab setup you can have it. But in 1986, a breakthrough happened. Okay, go to the next slide. 1986. All of a sudden there was a high temperature superconductor was discovered but it was high temperature, meaning it is higher than 4 Kelvin, but still very low temperature, 30 Kelvin. Then the next year, 87, they doubled the critical temperature, not double, 3 times, it became 96 Kelvin, and people got very excited more and more. Then currently we have temperature practical superconductors at 150 Kelvin, above the liquid nitrogen temperature, so we can have practical application using liquid nitrogen cooling superconductors. Liquid nitrogen temperature is 77 Kelvin. So 150 Kelvin is above liquid nitrogen. So we can have practical application using this liquid nitrogen cooling superconductors. And there are so many other materials discovered with higher and higher temperatures. Only in last year, 2020, okay, while we were people struggling with coronavirus, some people, scientists, they discovered the first room temperature superconductors, right? This is 14 degrees. Well, it is not exactly a room temperature, but above 0 degrees, that is good enough to be called room temperature superconductors. That happened only last year in October. So here we have some interesting demonstration of a superconductor. We have a permanent magnet floating above a superconductor. The superconductor is kept in a liquid nitrogen, so it remains superconductor. When you bring this permanent magnet above it, what happens? It will not allow the magnetic field to come in, so that superconductor become a magnet with the opposite pole, and it will levitate. It will, suspend this permanent magnet above it. So it's a very nice, interesting demonstration of a superconductor. So we are at the end of these slides. Done. So what do we do now? We're going to review what we learned by solving questions. I have already opened the midterm exam, midterm 2 of 2019. Let me open it. Okay, here we are. I'll go to question number 1 from chapter 17 and start solving them one by one. Okay, right. Here we are. Are you ready? Because you're going to do it, not me. You're going to help me do it. Okay, read the question number 1. Please, you should not be only listening to me, you will be looking at your screen. Are you, guys? Where are you? Are you even
Yes,
there?
doctor, we're here.
Okay, at least one person. What about the others? Abdullah? Faisal? Lulu? Lulu al-Bashar? Are you listening to me? Abdulaziz? Are you all sleeping or what? Abdullah? Okay. Abdullah Rashid? Abdullah Matan, fine, thank you. Jude is here. Abdullah Matan is here. Salman, thank you, Salman. Okay, Salman, tell me, how do you do this question? Can you tell me, are you reading the screen? What is in the screen? Salman? Salman, please answer. Yes, okay, tell me. Can you read it to me? Use the mic. Read the question, please, Salman. Use the mic and read it to the whole class. No, no, not solve it. Just read the question to me, to the whole class. Use the mic. Are you listening to me? No, you heard me before. Why do you have to repeat the question? I told you to read the question to the whole class.
A typical lightning bolt may last for 0.192 seconds and transfer 0 what
1.07
yes 1.07 times 10 to the power 20 electron.
electrons. Okay, you can skip what is in the parentheses. Continue after that.
Calculate the average current in A in the lightning bolt.
Thank you very much, Salman. Thank you. So
Thank you.
good. So you heard that, okay? Salman read it from the screen there. So question is asking about lightning. You know what lightning is? Lightning is the clouds get highly charged. So it has got a lot of electrons now. It can dump it into the earth, so you will see it as lightning, or it can dump it to another cloud nearby, so you can see the lightning traveling to the one cloud to another cloud. Or it sometimes not sometime, it comes to the earth as well. It can hit something and burn the whole thing. It's a very big charge. That is what lightning is. Now the question is, when charge flows, what is it? What do you call when a charge flows? Jude?
It's the current. When a charge
Current,
flows,
yeah,
it's the current.
current. So we are asked to calculate that current. So we have everything we need to answer this question. The current is the amount of charge and the time it took. The time is there, and the amount of charge, actually not the amount of charge, the amount of electrons are there. But each electron is a charge. And one electron has a charge of 1.6 into the minus 19 coulomb. Even that, you're being helped a lot. So he's telling you how to get the charge. You just have to multiply the number of electrons by the charge of one electron. So just there it is, right? You can just do the question. Say, I'm showing you the solution there. The current is equal to delta Q over delta T. Read the screen, please. I just scroll down. So delta Q will be the number of electrons in the charge of one electron. Divide by the time, you substitute and make sure everything in SI unit, it is. Then you will get the answer in amperes, which is the SI unit for current. Joule per second. Yeah. Yeah, tell me, Jude.
How do you do question 2? How do you do question 2?
You didn't do question 1?
No, I did question 1. I'm saying, how do you do question 2?
Oh, yeah. Okay, we are coming. Okay, going one by one. Okay, all right. Thank you. Let's do question number 2. So let me read here. This is a good question, okay? Because this tests another concept. Okay, the math is very simple, but it's not the math important here, the concept. In a certain material, there is 8 coulomb of positive charges per second flowing to the right and 8 coulomb of negative charges per second flowing to the left through the surface. What is the net current through this surface? Now, let's go back to the definition of current. The definition of current, the number of coulombs per second, right? How many coulombs flows per second? But the coulomb can be negative charge or positive charge. Isn't that right? Okay, the current can be due to the flow of negative charges, it is a current, or due to positive charges, it is also a current. So we can have a current due to flow of positive charges as well as negative charges. That's what something we have to understand clearly. So let me take a scenario. Say we have a proton flowing to the right, moving to the right. And at the same time, in a certain wire, or some material, an electron moving to the left. If I ask you what is the current now in that material, what is your answer? I'm waiting.
Can you repeat the scenario, please?
All right, okay. Let me draw it. Say we have a proton moving to the right and an electron moving to the left at the same time. Now, if I ask you, what is the current now in this? What is your answer? Per second, let's say, a certain point in time. So what is the current at that point in time in this material? Say it is at the same place, okay? So at this cross section, proton is going to the right and electron is going to the left. What is the current there at that moment? What is the answer?
For me, I'd say 0, but I think
Yeah,
it's
very good, very good. Abdullah, thank you, Jude. So you understand why? Because there is no net, because electron and proton has the same magnitude of charge. So one is going to the right, one is going to they're going to cancel each other, because whatever the current to the right is cancelled by the current to the left. There is no net motion of charge in any direction to the right or to the left. So the current is 0. So I want you to understand that. If you understand that, you can understand this question. Okay, now the question says 8 coulomb of positive charges per second flowing to the right. Now we need a convention. The convention is, maybe you forgot it, so let me repeat. Whenever positive charges flow, the direction of the current is the same as the direction of the flow of charges. Okay, did you observe that? For the convention is, whenever positive charges, the direction of the current is the direction of the flow of positive charges. So when positive charges flow, the current direction is the same as the direction of the charge flow. But when a negative, so that means whenever negative charges flow, the direction of the current due to those flow of the negative charges will be the opposite direction. Okay, this is the convention. You know what do you mean by convention? So people agree on something. This is how we are going to do things. That is what convention is. So with that convention, now let's do this question. So we have at the same time in a material 8 coulomb of charges per second. That means positive charges going to the right. So I'm going to call that current as I1 due to the positive charges. It will be 8 coulomb per second, mean 8 amperes, and its direction is to the right, because the current direction will be the same direction as the charge flow if the charges are positive. So I'm going to take the right side as my positive side, so plus. Did everyone understand that? For the first flow of charges which are positive, the current due to that charge will be 8 amperes and the direction will be to the right. Okay, so I put plus sign for right direction. I2, this is the current flow due to the negative charges. The negative charges are flowing to the left. Again, the same rate, 8 coulomb per second. That means the current is 8 amperes, but it is flowing to the left. But it means the current is to the right. So the current due to that negative charge flow will also be plus 8 amperes. Did you get it?
This is due to conventional motion?
Yeah, the second current is due to the flow of negative charges. The current is 8 amperes, but the charges are flowing to the left. That means the direction of the current is to the right. So since the direction is to the right, I put positive sign. So the second current is also plus 8 amperes. Is that clear, everyone? Or should I repeat it? Okay, you need some time to absorb it.
So
Look
even if
it's
a negative charge, even if it's a negative charge, it's flowing to the right. So that's why it's positive, right?
Now the negative charges are in this question, he says it is going to the left, not to the right. The charges, negative charges are flowing to the left at the rate of 8 coulombs every second. That means 8 amperes. But it is negative charges, so the direction of the current will be opposite. So this way we can get the net current correctly. Like I told you that example, when a positive proton and electron moving in the opposite direction at the same rate, the net current is 0. Because we considered the sign of those charges. So that's why they cancel. So in order to get that correct cancellation, we have to do this thing. So the first current is due to the flow of positive charges, and it is going to the right. Therefore, the current will be plus, because I'm choosing the right side as my positive direction. So I put the positive sign. And the second flow of the current is due to negative charges. Those negative charges is moving to the left. So that means their current direction is to the right, opposite. So the current due to the negative charges will be plus 8 amperes. Okay, I don't think I can make it any more clear. I just have to repeat what I said again. So I will stop there. Yeah, I think it is clear. Abdullah said it's clear. Thank you. Jude, is it fine with you?
Yes, it's fine. Thank you.
Thank you. So that means the total current will be plus 8 plus 8 plus 8 plus 8. So it is 16 amperes to the right. Plus 16 means the direction is to the right. Question number 3. Okay, now we have a question testing this concept in the next section. Okay, so we are covering all section in the chapter. 325 kilometer long high voltage transmission line, which is 2.15 centimeter in diameter, carries a steady current of 1610 amperes. The conductor is a copper with a free charge density of this electrons per cubic meter. What is the average drift speed, okay, of these mobile charge carriers? Now, you see the word drift speed, then immediately you should remember the concept that you learned. There is a connection between the current and the drift speed. Because current is a rate of flow of charges. Obviously, it is going to have some relationship with the speed of the charge carriers. The more speed means there must be more current, right? Because current is the rate of flow of charges. So we did really derived an equation. So you should remember that equation. Equations will be given in the formula sheet, yes, but it doesn't mean you just don't study at all. If you don't study at all, you don't know what equation to use for what question. Okay, you should learn the concept. This is not a course in math to test whether you know how to use the calculator. I mean, people in the school, grade 5, they should know how to use the calculator. If I tell you, okay, this is the equation, these are the numbers, find me the unknown, that is not physics, okay? That is not anything. It is just to know how to use your calculator. I mean, even if you're, I don't know, that's not what we are going to test. We are going to test how much physics you learned. So the physics here is the connection between the current and the drift speed. This is the equation. Now, we have been given everything we need except the drift speed. So we can substitute for everything else and find the drift speed. So let me describe the question again. We have a wire, transmission line, it's a wire. Wire has a circular cross section, so we need to know the area. And the length of the wire is given, but probably it is not needed at all, because in the equation there is no length of the wire. It is immaterial here for this question. It can happen. It doesn't mean, you have so many data, you have to use all the data in order to solve the question. Suppose you are not using one of the data, maybe it is okay. That's what it is, okay? Right, the area, is it given? Well, the diameter is given. So area of a wire, the cross section of a wire is a cylinder, right? Thin cylinder. The cross section of a wire is a circle. So do you know what is the area of a circle is? You should know, right? It may not be given in the question, it may not be given in the formula sheet even. This is again high school stuff. Okay, what is the area of a circle? Pi r square. Okay, so you are supposed to know it by heart. Okay, certain things you should know. Like, what is the prefix kilo stand for? I mean, I'm not going to give that in your formula sheet. Kilo, you should know it is 1000, so 10 to the power 3 and things like that. Okay, good. So we have the area because the diameter is given. So it is not the radius, what is given in the diameter. So you should know radius is diameter divided by 2. So the radius squared will be diameter squared divided by 4. What else? So n is given. So this is the n. N is the mobile charge carrier density. What is the density of this charge carrier? It is given. It is given in, again, number per cubic meter, that is in SI unit. So fine. What else we need? Q. What is the charge of one charge carrier? That is what Q is. The charge carriers are electron. The charge, the magnitude of the charge of the charge carrier is the electronic charge. That's also given. It's given here. Okay, right. That's it. I is given. Substitute, get the answer. Easy. Once you know the concept, easy. But again, some people, unfortunately, they know the concept, but they make mistake in the calculation simply because they don't know how to use their own calculator. I allow you to bring your own calculator. So you should know how to use your calculator without making mistakes. Sometimes it is because they don't know how to handle the exponent. Okay, that's bad. I mean, you should be ashamed of that. Okay, right. Don't make such mistakes. Question number 4. When you flip a switch to turn on a light, the delay before the light turns on is determined by, you know the answer to that, right? It's a concept that I stressed while doing that simulation, right? We looked at it through the simulation, and you know that when you turn the switch on, the light comes on immediately, almost instantly. If you think the electron that is coming out of the battery from, say, from the negative terminal of the battery, it has to take the whole journey through the resistance of the bulb filament and come back to the positive terminal of the battery, complete that round journey. Then it is going to take a long time for the bulb to light up, because the drift speed is the speed with which the electron is going to move around, and it is very small speed, and you are not going to expect the light to come on the moment you put the switch on. So why it doesn't happen but it happens instantly? You know the reason. The electrons are already there in the filament, the free electrons, ready to move the moment it sends the electric field. So what is important here is the electric field to travel through the circuit, and the speed of the travel of the electric field is the speed of light. Okay, electric field is electromagnetic wave. So light is an electromagnetic wave. I hope you know that. So the speed of electromagnetic wave is the fastest speed possible, 300 million meters per second. So that's why we see the light bulb lighting up immediately almost. The answer is D. Is that clear? Okay, let's go to the next question. Again, an easy question, just straight question, direct question on the definition of the Ohm's law, the definition of resistance. You measure a 20 volt potential difference across 8 ohm resistor. What's the current? There it is. Okay, just substitute. Okay, easiest question ever. Next. Okay, again, another easy question. What is the unit, SI unit for electric current? Okay, the SI unit for electric current is actually joule per second, right? I'm sorry, coulomb per second. From the definition, what is the current? It's ampere. It is called ampere, but it's actually coulomb per second. How fast the charges are flowing across an area. Are you all with me? Okay, please. Jude, you got tired? Yeah, Abdullah is with me. Okay, Judy is again here. Hi, Jude. Okay. Where are you? Jude Imad. Why did your name change again? Is it Jude? Jude or your twin sister Judy? Judy, how are you? Never mind. Okay, so it is coulomb per second, but we can get an equivalent unit, SI unit, in terms, because of the Ohm's law. Ohm's law tells me the current also can be given in this unit because delta V over R. So we can say it is volt per ohm also because the coulomb per second is not there. So this is incorrect because it has to be volt per ohm. This is the resistivity unit. This is not coulomb per second, it's coulomb per meter. That's also gone. This is also wrong because it's volt per ohm from the Ohm's law. Right. So we have an alternative unit. It is same as coulomb per second, alternatively expressed in terms of ohms, volt per ohm. We got another question, again direct substitution. A certain laboratory experiment requires an aluminum wire of length 28 meters and a resistance of 3.5 ohms at 20 degrees. What diameter wire must be used? Well, the question has not been done for some reason, okay? Well, only the equation is given. So it's based on this equation, the definition of resistivity. So the resistivity is given to us at certain temperature because it is done in that temperature, because it can change with temperature. So anyway, we can just ignore that because we keep the same temperature. So the resistivity is given to us. The length of the wire is given to us. The resistance is given to us and is asking for the diameter. Now, you know the resistance and resistivity are connected through the length of the wire and the cross-sectional area of the wire. But he is asking, he is giving us resistance, resistivity, the length, length, and he's asking for the diameter. There is no diameter here, but there is a cross-sectional area. But you know, diameter is related to the cross-sectional area through this equation. So that means I can substitute what is given to us and find what is unknown, the diameter. Okay. So this is the answer. Please check it. Number 9. A wire 2 meters long and 0.25 millimeters squared in cross-sectional area has a resistance of 40.5 ohm at 20 degrees Celsius. If its resistance increases to 43 ohms at 30 degrees Celsius, what is the temperature coefficient of resistivity? Again, direct substitution into an equation. The equation is this. That gives you the resistance as a function of the temperature. This is the resistance at the reference temperature, and this is the resistance at another different temperature. All these are given to us. The resistance at reference temperature is given. This is the R0, and this is the T0. And the resistance at another different temperature is given. So R given, T is given. R0 is given, T0 is given. And you are asked to find alpha. So it's just a direct substitution into the equation and solving for the unknown alpha. Right, okay, guys? So is that clear? I can't do this because, you know, if you don't respond to me, it's just like talking to myself. You know, I don't have any motivation to continue. I don't know if you're listening to me or maybe just doing
Doctor,
something. You're listening? Okay, thank you. Please give me some feedback time to time, okay? So that question is clear, right? But again, you know, some people having difficulty doing simple calculation. This is not acceptable, okay? This is not acceptable. You should be able to do the calculation without making any mistake, okay? You have a calculator, okay? Even the calculator can even do solve, you know, the calculators that we have now. There is, you can give the equation to the calculator and ask it to solve, you know, that making your life even easier. If you don't know how to do it, you know, please, you know, ask someone who knows it. Okay, you can ask me if you want to, not now. Okay, let's go to the next question then. Number 9, the potential difference across a resting neuron. Again, you know, the questions are just, you have an equation and you pick which equation to use. It's just substitution and find the unknown. Very easy questions. Potential difference across a resting neuron in a human body is 82 millivolt and carries a current of about 0.340 milliamperes. You know, you see, even our human body, we have electricity, okay? Of course, our brain is just functions with electricity. You have what you call electrocardiogram for the heart, EEG, electrocephal or something for the brain head. We have electricity. We communicate through nervous impulse. The nervous impulse are electric current, nothing other than electric pulses. So here we talking about a neuron in the human body. Neuron are the brain cells. Okay, I think so. Yeah, nerves. It is small voltage, but significant. Okay, we think using electric pulses. It is 82 millivolt, okay, 1,000th of a volt. And a current is also in milliamperes. What is the power? So you just have to remember the equation for power. I delta V. I is given, delta V is given, substitute, get the answer, done. Simple. Another very simple direct substitution question. But remember again, okay, if you don't know the concept, you don't know which equation to use. Okay, there is no substitute for studying. You have to study. There are no shortcuts. Okay, the last question, and we can stop. 650 watt heater carries a current of 4 amperes. How much does it cost to operate the heater for 40 minutes if electrical energy costs 4 halalas per kilowatt hour? So we charged for the energy consumption, how much joules you use. But however, joules, as I said, is a very small unit of energy. So the practical unit is kilowatt hour, not watt second. Okay, watt second is the joule. So we are given the price. 1 kilowatt hour, you have to pay 4 halalas, a very small amount. I don't know whether it is the actual cost, but I just put some numbers. It doesn't matter. So how do we calculate that? See, we are using a 650 watt appliance, a heater. That means this appliance will get the energy at the rate of 650 joule every second when you connect it to the power supply. And it carries a current of 4 amperes. Now we have a way to get the energy. Energy is the power multiplied by the time, right? So the power is given. So let's get the power in kilowatt hour. Why? Because, let's get the energy in kilowatt hour because the cost is given in kilowatt hour. So in order to get the energy in kilowatt hour, I'm going to substitute the power in kilowatt and the time in hour. So I will get the energy not in joule, but straight in kilowatt hour. So we think cleverly. Just without getting the energy in joule, then converting it to kilowatt hour, we will do the substitution for power in kilowatt and substitution for delta T in hours, then directly we will get the energy in kilowatt hour. So that's what we do now. So power is given as 600 watt. I convert it into kilowatt, so it will be 0.65. And the time is given in minutes. I convert it into hour. You just divide by 60, not by 3,600. If we divide by 3,600, it becomes second. I don't want it in second. I'm sorry, if you multiply by 60, it becomes second. But I want the minutes in hour. So you divide by 60, it becomes hour. So when you do that, we get the energy as 0.433, not joule, kilowatt hour. Now, the next step. That is not the question. The question is not to find the energy, to find the cost. The energy is 0.433 kilowatt hour, and we know 1 kilowatt hour cost 4 halala. So you multiply the rate 4 halala per kilowatt hour by the amount of kilowatt hour, you get the answer 1.7 halala. And we are done. Well, there are more questions, but 10 questions from chapter 17 in midterm 2 and 10 questions from chapter 18. So we finished chapter 17. So we have no more questions. Question 11 is on chapter 18. So any doubts? Can I end? We still have time, but I have run out of questions in this. So I'm going to stop unless you want me to do something. Any question, please? Guys, please answer. Where are you?
All clear. Thank you, doctor.
Okay, thank you. Right. Okay, Lulu. Okay, I'm going to end the session, or then you will be. Okay, Lulu, you want to ask me? Okay, I'm in the classroom, so you cannot call me. What is that you want to ask me, Lulu?
Doctor, I wanted to talk to you about the situation of Sunday when I didn't attend the exam.
Yeah, but I sent an email. You can reply to me because I told you the exceptions are those who were exposed to the infected students. So those are the ones who are eligible to take the makeup exam. In your case, you are saying something very strange. You said you are exposed to someone exposed. That is not good enough. You should have attended the exam. Anyway, I don't want to talk now publicly, okay? So please answer my email. I will reply to you, okay? Right. I'm going to have the makeup exam for those who missed this exam because of it's not their problem there. So that will be next Wednesday, okay? So now let me end the class. Thank you. So
Thank you, Doctor.
thank you. I should end.